Let us consider this candy jar represents a population of candies, just like a real life population of human beings. And different colors of candies represent diversity of that population. And each color being a characteristic of that population. Like in real life population, these characteristics can be related with skin color, race, religion, gender, or any other thing like that, which will define that specific segment of the population. If you notice that each of these colors have a certain proportion in the overall population, we call it proportion. Like, for example, if we look at the proportion of yellow candies in that jar, it is represented as p, small p, and it is calculated as number of yellow candies in the population divided by total population, or in this particular case, the total number of candies in the jar. We can use this proportion to describe population, and we know that the numerical measure that is used to describe population is called as parameter. So we can call this proportion a parameter for this population of candies. And we know that the parameter is described with a statistic, and in this particular case, for proportion parameter, we have sample proportion, which acts as a statistic. It is represented with p and cap on the top. And now we can consider that we take a sample of candies, means we take a few candies from the jar and consider it as a sample. Then we can calculate the sample proportion p cap of yellow candies in that sample. And to calculate that, we have p cap is equal to x divided by n, where x is the number of yellow candies in the sample, and n represents the sample size, or the number of candies that we have drawn from the jar. Here x is a binomial random variable because it has only two possible outcomes, and we know that for binomial random variable, the distribution is called as binomial distribution. And for binomial distribution, mean is equal to n times p, and standard deviation is equal to square root of n times p times q. Okay, now here this sample proportion p cap is a variable which is similar to x, binomial random variable. Therefore, its distribution, its probability distribution will also be similar to the probability distribution of x. And since x is a binomial random variable, its distribution will be binomial random distribution, of course. And if we draw this distribution, if it looks like this, 0, 1, 2, 3, 4, and 5. This is the sample size. There are 5 samples, and x-axis is the variable, binomial variable x, and y-axis is the probability of that. Then p will just be another axis along the horizontal direction, and it will have only different values because it is the variable x divided by the sample size, just like this. Since it is similar to binomial random variable, its distribution is also similar to binomial distribution. Therefore, distribution of p variable or sample proportion, which is equal to x divided by n, the mean will be equal to n times p divided by n. N times p is the mean of variable x, but because p cap is the variable divided by n, we will divide this mean with n, and standard error of p will be equal to square root n times p times q divided by n, and it will become p times q divided by n whole square root. So these are the two formulas for probability distribution of sample proportion. Now we can approximate the sampling distribution of p using normal probability distribution, but we can use this approximation only when n is large. Means we can estimate that when the products n times p and n times q both are larger than 5,